Okay, so the presentation is advanced dam analysis and the enduring role of engineering judgment using FEA and X. The project I'm going to go through, I'm only going to cover the aspects of seismic analysis and then just something about sliding stability. I haven't covered aspects like thermal analysis or detailed stage construction. So it's not a complete review of the dam analysis. Yeah, so I'll give a short introduction, and that's just to discuss the geometry of the dam and how we'd expect it to behave, and then just a slide on the stress paths, and then the seismic analysis, sliding, and concluding remarks. So we do very detailed analyses. We saw in the previous presentation how many options and how advanced it is and automated. But at the end of the day, the models don't make the decisions, the engineers do. All we've been given now with these tools is more data, more information to make a more informed decision. Modern analysis tools offer the insight, as we've seen, but require professional and experienced interpretation. The topic of seismic analysis talks to understanding seismic performance under realistic demands, and the sliding stability will just cover Monte Carlo simulation to quantify uncertainty at the interface between the dam base and foundation. A similar approach can be done for abutment stability as well as lift joints. So, I don't have my glasses. I'm going to try and get that table. But essentially, this dam was was actually completed in 1941. So it's aged infrastructure. And I think there's similar dams. This one's in Australia. There's similar dams throughout New Zealand. And I think as soon as you see that date, you automatically say, that was far before anything we have today. So there's a structure standing there. Did they design it for what we design today? And could they have designed it? In terms of seismic analysis, I think a common way to model hydrodynamic mass is using Vestergaard's added pressure or added mass. And the formulation of that just came out in, I think, 1933. So I don't even know if that was widely accepted at this date. So whether they designed it for seismic or not, given this is in Australia, is even a question. It has an upstream radius of 61 meters, crest length of 115, approximately 21 meters in height, and a base of 6.4. So we look at some ratios, and the length to height ratio is a 5.5. They are generally accepted numbers, especially in the engineer's corp. It gives some guidance to that. And then the base width to height also gives us an idea of how we can expect it to behave. The dams the old dams even dams today were pretty much designed on rule of thumb in terms of, or the set out in terms of your angle to abutment from the center of radius, that sort of thing. So you get fairly similar ratios within a range. I think this one, you can see the length to height ratio is, it basically will dictate a shallow curvature and reduced arch efficiencies, which we'll go through in the stress plot. Thank you. You saw me squinting. So the geometry is it's a U valley shape, which again would lead to what you'd expect with stress flows. And the base to height ratio is 0.3. If you look at it by eye, you'd say it's a thin arch, which essentially it is. But if you can get thinner arches in a narrow V valley, and for this particular geometry, we'd expect the approximately upper 2/3 to have quite horizontal arching in terms of its principal compressive stresses, with the bottom third, 25% to third, being cantilever in terms of tensions, vertical tensions on the upstream and vertical compressions on the downstream. So again, before we've set out any analyses, you got this in your head what to expect. The design considerations, I've written foundation stiffness, uplift control, temperature, and contraction effects. Contraction effects is generally due to thermal drops. Luckily in this case, it's in a fairly uniform temporal climate, and generally in the olden days, they didn't build as quickly as we do. So there was quite a time duration between lifts, or a slow progression of building. So that also helps the thermal drop load case. I got lots of time. So I want to go back here. When we go to site, there is one thing we look at. We observe the structure, and there are particular points that you look here. You'll see, for example, on the one, there's seepage, some lime deposits. Now, when you observe that, before you go back, you can also say those lime deposits would affect the interface or the lift joint strengths parameters in terms of friction, cohesion, and you can actually spot that across the entire dam face, and you can see spots are more concentrated than others. There's also seepage on the downstream apron, which shows you there's pore pressures, artesian pore pressures. So the uplift function is not going to be exactly like design. So just by observation, you can make these prejudgments of analysis. For example, there's deep bonding at the top. I could expect quite a lot of arching stresses to be there, and that would probably cause that debonding. So now we look at, this is just under hydrostatic load, so nothing else. And we go back to it now. And these are the principal compressive stresses. I know generally when people look at it, they look at the horizontal or tangential, otherwise referred to arch stresses. But I do primarily look at your principal compressive and principal tension stresses. Now, you can see, as I said previously, the upper 2/3 is pretty much a hoop stress there, very horizontal. And automatically that tells me when I look further that even if I get a vertical tension there, it's not necessarily the worst thing in the world because it's acting in hoop stress. So the only thing there that would really be significant is if there's a shear failure between those hoops. You don't get continuation of the arching. Then I haven't put this in there, but the the principal tension stresses on the upstream would be vertical. So just from looking at this, the model replicates what we could expect, and that's a positive outcome from the get-go. That's before we've gone any further. A key point to the construction here, and it's actually quite common in the olden or the older dams, arches, or thin to thin medium, is the keen, the pocketing. On others, there's actually discrete shear keys that they put in there. And that's why you'll see one of the biggest things on an arch is to try and ensure you don't undermine or deteriorate the downstream foundation of the center monolith. And then another key point is the shear keys. So those are the vertical joints that have a shear key. So again, you want locking in of that hoop stress. So those are generally things we'd want to move forward and check. Again, going for the seismic analysis, I generally have an equation in my mind. That's the equation of motion. We have your mass, your acceleration, your damping, velocity, stiffness, displacement, and that's on the left-hand side. So the way I see that is that's my model. That's my FEM model, my material parameters, my geometry. And then obviously damping. Damping is a very important one. I know there's rules of thumb, as in if you look at an operational basis earthquake, you use 5%. If you look at a safety evaluation earthquake, you use 7%. But it's wide. Well, it can be debated because there is Anil Chopra who has shown from testing on site that it can be as low as 2 to 3%. Again, that's prior to any significant damage. So that's a very important factor that can't really be pinned down straight away. And that's easy to define. And all of us define the FEA model on a day-to-day basis, whether it be a bridge or pushover, anything like that. Now, the key thing that we sometimes put a little bit less effort into is that acceleration, the seismic acceleration, the signal selection. And that's the one on the right. You can start with the response spectra, but for arches, for evaluation of existing or anything past feasibility, time history is the way to go. You shouldn't do response spectra on arch dams. So we're going to move forward on just a short discussion on that acceleration and how we look at it. So what we do is we take a target spectra, whether that be a conditional mean spectra, elastic spectra, whatever it is, and depends on why we chose it. That's our target spectra. So we will then go through a catalog of signals. You can select synthetic signals, not preferred, but you go through a selection of natural signals depending on the geology, the fault type, the VS30, the PGA, and you basically select signals that have a fairly similar profile to your target spectra. Then from there, it's never always on your target spectra. So following that, you need to actually look at frequency matching, which is what you see there. The blue line is the original, and this is only for one event. You normally select 3 to 4. The blue line is the original signal, and then the green line is the frequency match signal. Now, I've written there massless and mass foundation. So massless foundation is been the way people have done it in the past. We're all familiar with it from a dam industry point of view. The benefits of that is that you don't get wave reflection and you don't get signal amplification or change in frequency of the signal. But you also don't get a fully accurate capture of the dynamic response of the system because you forgot out some of the mass part and some of the, so you generally don't get the exact same representation of a dynamic response. So I've written there for the mass foundation, we need to now be careful of using, although we've selected the signal with frequency matched, we need to be careful of what we're actually inputting into the model because the foundation, having a mass now, has its own resonant frequency, which you can see there. That's for like a column of swirl, just to give you an idea. So that was what, 4 and 3. So 3 is for the upper abutments, and the 4 would be generally below the dam. And note there's 2 different, so you'll get 2 different signals in the dam. And that's the stars shown there. So that's also a question in terms of judgment. Which one do we then target? Do we target the point at the base of the dam, or do we target the point at the abutments? So you can see the magenta line is basically if we take that matched signal and we run it, we can see we get quite a bit of amplification there. Which essentially we could say, okay, we matched it, we put that in at the base, everything should be fine and dandy, but we're actually exposing it at the top or at the foundation to a much higher signal than it should be. So what we need to do is we need to relook at it. Now, the mathematically correct way and geotechnically correct way is to do deconvolution. So essentially, you develop a transfer function which says to, in layman's terms, it says, I have this input signal, or I want this signal at the top to be X. I have X, or depends, whatever layers of foundation you have. What must be my input signal to get that? That's essentially what it's saying. It's very difficult to do in 3D. So generally we do a 1D site response and deconvolution. But again, once you use that, you put it into the 3D model, you actually don't get it. So we need to now use judgment and say, do we, from a project point of view, do we go through that entire process, which can be quite cumbersome, specifically for, I'll deviate a little bit now, but quite importantly, do we do this for an isometric rock foundation? Theoretically, you have to, but from a project basis and judgment, you can essentially descale the signal. And you can see there that, I can't read the legends, but essentially you can see that once you descale it, you can bring it back to the spectra. There'll still be an amplification at the natural frequency of the foundation. But in the realm of the foundation reservoir and dam, that period is within the spectra. And for dynamic amplification, generally you'd want to take 0.7 of the forcing frequency and 1.4 times the forcing or the period of the structure. And if it's outside that band, it doesn't have as big an influence. So you could use that as a rule of thumb. Coming to deconvolution and selection, I've got lots of time. If you have, and this is particular for New Zealand with softer swirls and larger events, you can't take a spectra from a code. I think the Geotechnical Society might like that I'm saying this, but essentially you have to look at shear strains and plastic response of the foundation. So what one should do for complex geology, and that's why it's important knowing what geology is there and how it behaves apart from liquefaction, is you need to run a 2D analysis, because if you put, say, a G signal or 0.7 PGA seismic event in there, that 0.7 might not even reach the top because your shear strains might be so great, your swirl damping is large and it doesn't carry the signal up. But what it does actually do is it goes through period lengthening, or it changes the frequency content of the signal. And that's critical to know, and you can't capture that in a response spectrum from the code. Okay, that's my deviation. Now, what we do is we then, before I run the dam analyses, I run the analyses or time history on the foundation by itself without the dam, because the principle is you want to expose the dam or structure, whether it be a building, whatever it is, to a signal or that would be on foundation without any structure there. That's what it's doing, because the seismic events are generally measured at stations, which should not be too influenced by anything else. Okay, now for this particular dam, and you predefine how you want to model it, but for this dam, what we did is we split it into different monoliths, different lift lines. That's why there's a nice color plot there. Then we create the foundation dam interface, because that's one of the things I want to assess. We have vertical lift joints, because we want to see that engagement or disengagement. And then the bottom bit is it all put together. So it looks like quite a complex model, which it is, but what I found is advertising for you guys. What I found good with MIDAS is it's got a very powerful automesher compared to other softwares I've used. The key is making sure your geometry is done, taken time, done correctly. And that I'll stress that with any FEA. Geometry right in the beginning is very key to saving time throughout the entire process. So if you do that right, you're pretty good to go. Now, in terms of not the interfaces, we have the dam. we have the foundation, and we have the reservoir that we put in there, the sloshing elements. What I haven't shown there is the free field elements that do also come on. Critical for arch dams, or even for gravity dams that are in quite a narrow valley, is doing a staged analysis for gravity loads. I have witnessed on projects where they don't quite do this. Funny enough, it was actually a gravity dam and in a fairly narrow valley. So if you put the dam all once or even two larger intervals, you actually get an arching stress under gravity load, which is incorrect, and then the rest of your analysis is incorrect. But it is definitely key for arch dams. And you can see there we go to stage 1 to 8 is once the dam's built up, and then we have hydrostatic loading or your design loading, and following that is the seismic loading. Advertising, the stage construction analysis is actually quite easy to set up, which is nice. You left with a lot of time to do engineering rather than analysis. You do VNV, you do your checks, but it does give you that time in projects to do the engineering. Okay, so here's some pretty pictures. On the top left, it's actually an extract from FERC. Do note this isn't exactly the same kind of arches. This would be a V valley or narrow valley, possibly. And some of the things you want to check is, as you've seen there, the vertical interfaces, because if you lose that, you lose arching, which is essentially the stability of the dam, and your horizontal cracking, which would be your vertical tension stresses. So to review this, again, knowing this is what we want to do, we've already modeled the dam with interface elements. There is a shear key in there. So the interface elements, what's nice is you just leave the shear stress or shear strength elastic, and check it afterwards, but you leave it elastic. The normal stresses, you can do elastic, perfectly plastic. Generally, I put the tensile strength at a nominal 100 PA or 1 kPa. It's not a massive deal. It converges quite nicely. And on the top right is going to be, that's the principal tensions. So I'll just talk you through that. The bottom left is the relative opening in the normal. So we can, throughout the time history, tell what's happening. You can also do it in post-processing, but this is nice and visual for a presentation. The bottom right is, I've put that in there because it's a nice little check. So that's an extraction of the hydrodynamic pressures, or the pressures on the interface between the dam and the reservoir, just the time history of the pressures. And you want to check if the model is right, and you want quick little checks. We have in-house tested with my colleague, might be watching, Ryan, that it does actually model the dam and the hydrodynamic pressures accurately, and we benchmarked against I think it was a 2019 benchmark workshop problem for Committee A of ICOLD. So we did look at it again, check in your work, and that gave good results compared to the widespread that you actually get. It was quite accurate. But for project specific, we basically, what I did is I took the Vestergaard's equation, calculated what your peak stress would be, equivalent. So you extract your acceleration at the heel of the dam. Then you put in Vestergaard's equation, and you say, okay, where does our time history match with this? And you can see it's not exact, but it gives you a pretty good approximation. I don't expect it to be exact because Vestergaard's formulation was based on a rigid dam. Arch dams are extremely flexible, So you can't get the same, but it does give you some form of confidence in what you're getting. Here's my little videos. So this is going to be the relative opening, and the shear keys that we saw previously was approximately 150 mils. So now we can basically look at it and say, are we getting 175? What are we getting? And this is with the 0 tensile strength interface. So you can see we do get some opening at the top portions, but I think that's probably like, what's it, 2 mils or something, quite low and well within the capacity of the shear keys. Also oscillatory in nature. It's not constant. So by the time any debonding could happen under 0 tensile strength assumptions, it's re-engaged. So that's one check we've done now. And then another one that I'll talk. So this is the principal tension stresses. And you'll see they actually do get quite high. But one check that I am going to do probably in this next week is the lift joints. I'll assign a 0 tensile strength. And basically what you're going to see, or what I'm hoping to see, is the rocking effect and how it rocks. Because you do get on the downstream toward the upper portions, you get quite high vertical principal tensions. So you'd expect some lift joint opening to occur. And at the base, on the heel, you also get high vertical tensions. And that'll be debonding. But that, at the interface of the heel, when you get uplift and it peels away and you get increased uplift load and it peels away, essentially what that does is it throws more arch stress into the abutments and less shear demand on the center monolith. Less so with the wide U valley, but it does nonetheless. So that's just a couple of nice videos. Yeah, so look, there's a lot of other checks we do, but this is just for this presentation. So don't take us as I did these checks, the damn's fine. There's a lot of other checks that go into it. Okay, now one thing I want to cover here is, and then I think we need to give it consideration. It's sliding stability, and like I said, it doesn't have to be just the foundation dam interface. It can be the abutments where you get thrusts, lift joints, wherever you want to check it. Basically, in dams, what we do is we take a look at your peak pressure or peak strengths, shear strengths, and your residual shear strengths. And we check it and we get different, this is for gravity specifically, we get different factors of safety and there's different requirements in the guides. For the arch dam, you can see there this is out of USACE. You get for your usual static, it's 2, for unusual, it's 1.3. So essentially you choose a friction phi and you then go and check the case. Fairly simple. Now, you've made an assumption on that, but there are so many different variables. Is your jointing, your orientation, your joint orientation in 3 dimensions, how well it was constructed. You can see, for example, there, the disparities that you have. If under low normal stresses, it would have to ride those ridges to fail in shear. Under high normal stresses, you'd have to shear through that entire rock portion. Again, that's only because those joints are orientated as they are. You need to know your joint orientation. But this again points to the importance of engineering judgment, because we have a model that's a continuum, linear. We can do nonlinear, but I'll get to that point why nonlinear is important, but also can't be fully the end goal. So what's important, and I'm sure a lot of us have looked at this, is we got Moore Coulomb envelope. Now for rock or concrete, what have you, or in the interface, the actual curve of the Moore Coulomb is nonlinear. It's not a peak and a residual. Well, it's not linear. We want to understand at what pressures the structure is being exposed to. You can see there, depending on where it lies, your friction angle actually changes, your cohesion changes. And the interface between the dam, the concrete, and the rock is often stronger than, or very often stronger than the actual localized joint you might have just below it. I've actually seen that through coring. We've cored through this dam actually, from the downstream right to about the middle of the interface, and we've got some decent cores. So what's important to quantify when we looking at this, particularly for concrete on rock, that's what I'm talking about here, nothing else, is we want to capture our cohesion. We want to understand what our phi is. These are the variables. That will give us the first line. Then, as I said, because the interface between the rock and the concrete is often extremely competent, there is a direct tensile strength associated, and that's that blue portion there, which then we can define the other portion of our material parameter. So what happens now is we've extracted the interface elements, all the details in terms of the coordinates. And again, it comes to setting up your model. You don't want your model in an arbitrary position because then it makes the rest of your post-processing difficult. So you set it up in the beginning. So understanding the structural response of the arch in terms of we got high compressive stresses at the toe, we've got low, or we've got tensions at the heel, and that could actually, due to the arching, and it depends on the shape of the valley, we can assign different zones. The zones can be numerous. If we do have a geological feature running one abutment of the dam or whatever have you, you can replace that with a different zone, a different material parameter. Again, this is all post-processing, but the post-processing is easy due to the ease of extraction and the compatibility with Excel. It would not really be as user-friendly if it wasn't. And for MIDAS FEAX, I'm looking forward to the API so I can do something that Willem's been doing. So what we do is we assign for the friction, for the cohesion, for the tension, we assign the mode, the min-max. This is in particular is for a triangular distribution. The key here to this whole procedure is defining your zones and defining your material distributions. That is quite an important factor here. And now these come into a lot into engineering judgment, because a lot of the times with existing dams, there's not a lot of instrumentation, not a lot of geological or geotechnical testing goes into it. I was actually very impressed with this client, his willingness to actually undergo or undertake drilling and testing. So I'm looking forward to that coming back, and I can define these a lot more accurately. So I think we all know Monte Carlo simulation. Essentially what it is you've got your distribution, a cumulative density function, and you use that to just randomly sample points, and those will be done for the zone. So we have our results extracted from MIDAS. We've chosen our distributions. We've got our material parameter, or our material strengths that I just went through now, and you can see the parameters there. And we basically calculate the shear, the sliding factor of safety for each as we go in iterations. I think we've got pretty good convergence at about 5,000 samples. which wasn't too bad. These are just the distributions. So I think what would be an important part of following this process is once we get to the stage, we sit as a group of whoever the designers are or the checkers, and we sit and we say, these are the distributions we decided on. This is the reasons why, whether they be from geotechnical reporting, testing, or sensitivities, very experienced engineering. I mean, guys that are in their 60s, that kind of judgment. Not a, with all due respect, not like a 20-something-year-old, because you do need a lot of experience with this. And at the end of the day, following all those calculations, you can get, it's basically 1 minus the cumulative distribution function. So if you read off the y-axis onto the x, it's saying there's an 80%, let's take for example, which is a nice one, I can't quite see. But if you take 0.8 across and down, that's saying there's an 80% probability of exceeding that factor of safety. What's beautiful about this as well is you get to understand the variability that's per monolith. And again, if understanding that the center monoliths, if they do weaken, they actually distribute that load to the adjacent monoliths, because we check the shear keys and they transfer quite nicely. And you'll bring the more robust monoliths, their factor of safety will slightly fall, and the central monoliths would increase slightly. Now we compare that graph to what would have been done in the past is we take the best estimate, or maybe our peak, let's call it the peak, and we take our residual, and we'd find 1 factor of safety. But are we able to speak to ourselves and say, okay, well, where do we stand? How's our feeling in terms of how does it change? What can we expect? We can, but I also find this a lot more helpful. And in particular, one reason it's helpful is what's coming to play a lot more, and this comes to business decisions, is risk assessments. So they are very advanced. You got risk specialists that do this huge risk assessment, event trees, whether it be seismic, floods probably for Australia. And they've got these probabilities, and then eventually you do a seismic analysis. And what I've seen in the past is you do your analysis under an event. Let's say it's let's call it sliding for an event, and then there's a table of may happened, would happened, will happen, and then it's got a qualitative probability associated to that. So then what you do is you look at it and you say, you know what, I have an idea that it would fall into this category, and that goes into the event tree. And that actually gets used to make business decisions by owners, which is critical, because then we turn into money, infrastructure, where you assign your resources as a business. So this is one place where it would be powerful, because you could say my factor of safety required by the code is 2. What probability would there be that this could fail? And that could be used directly if the sliding stability is the driving failure mode I'm talking about. You could directly read that off, and that would go into the risk assessment. And it's a lot more educated guess, I'd say, or scientific. That guess was a bad word. It's a lot more scientific approximation. So I do believe that this should be embraced a lot more. I know some people do use it, but I would want to bring attention to it. And it's not only used for sliding stability, it can be used for a lot of aspects, anything essentially that you've run a linear analysis on. So my concluding remarks, I think you can see now, if you set it up correctly, you know exactly what you want in the end. FEA NX enables a deep insight into dam behavior, which allows one to make informed decisions and interpretations of your structure. It's fit for purpose modeling approach. You can go extremely complicated, which sometimes I do, but I try and not do it unless it's required. For example, I will do it if I really want to understand how I've looked at the probabilities and I've said, okay, this is the friction and phi I want to analyze it under. And you do a full nonlinear and you actually go to a failure mode. And you want to see how it responds fully. That's one way to do it. And it gives a very balanced perspective between detail, practicality, and computational effort. Because computational effort is two things. It's the cost of the project, and the more computations, the more time you spend doing the analysis due to commercial limitations, the less time you have to actually do engineering. And then we can distinguish, or know in the judgment, you distinguish between physical response vis numerical artifact, something that's produced, for example, a stress concentration, which I've also come across where we get a stress concentration and there's a real panic about it, but you can understand that is a concentration. And analysis informs, engineering judgment decides. So if we go straight away from linear analysis to nonlinear, or some people start with nonlinear, you got one data point. So your analysis informed one data point. We are leaning more towards quantifying reliability and I wouldn't say not deterministic safety. I would rather actually say which complements deterministic safety. I'd say it's a complementary and interchangeable relationship. And advanced analysis is a tool, and engineering judgment is the craft. And lastly, thanks to MIDAS for appreciate it, and Engineering New Zealand. Thank you very much.
Thank you. Stay there. We've got 4 questions online that we'll pose to you now.
Given that the earthquake motions database are relatively limited in New Zealand, what are the implications of taking overseas time history records in terms of frequency components for different rock properties?
So, for example, if you just take the west and east coast of America, they're completely different geologies. The west coast, I've interchanged, but the west coast is much more seismically active. I mean, you've got the San Andreas Fault. I think it's one of the biggest ones there. So for New Zealand, which is also seismically active, you just choose which database you want to sort of use. But more importantly, it's the fault typing that you want to look at. And that's what you want to then match it to. And also the VS30. That's one aspect you want to do, which is a search criteria, and your earthquake magnitude is quite a good one. But when selecting, I'd also look at the Aries intensity of the signal. Generally, a slip strike gives quite a high one. But once you've got your target spectra, you can frequency match that, or you alter the signal. You just try and keep that to a minimum. That's the goal. You keep that to the minimum so you don't change the signal too much. Did that answer it?
Sounds good to me. A follow-up question. Is it difficult to find time history records with similar site to source distances and similar ground properties?
Not really. I know Europe, I think it's EMS has one. They've got quite a good database. That's actually another criteria that you can use is the epicentral depth. And is it PEA in the States? I think it's PEA. It's University of Berkeley, California. I think they've got a research center that has a database that for minimal fee you can actually subscribe to. I think EMS is actually free. So yeah, you can get them. It's just, sorry to carry on, but when you do it, There are a lot of them. So you got to do it wisely, and generally there are systems out there to do that for you.
Thank you. How do you verify your ground amplifications are correct in a New Zealand context?
Well, I don't think it's only a New Zealand context, I think it's a world context. I think, as you said, or as I showed there, I'd look at I model it without the foundation, and I first establish what signal will be my structure will be exposed to. I think I also touched on, in terms of New Zealand context, is if you do have lower strength material, that I would recommend doing a separate analysis. Specifically, at the moment, I'll just say it in like Plexus or something else like that. Flak's a good one. That's a finite difference, I think. I'd actually have a specialist geotechnical team look at that to develop the signals and go from there.
Thank you. That's all.